Okay, we're going to do some homework sample problems. I know, especially with period 3, we ran out of time going over all of these problems, so I'm not going to do all of them. I'm just going to do a couple of them. That way, for those of you who didn't know how to do it over the weekend, you have another shot at doing it. It needs to be complete. It needs to show all your work. And I will stamp it with a different color and a little designation, and so you will receive partial credit if you redo homework number 9, if you didn't get it stamped, and you show all your work. So I'm going to do a couple, like I said, I'll do a few of the problems. So we're going to start with a 27B. It says to calculate the pH of a solution of a 0.1 molar sodium propanoate solution after 0.020 moles of HCl is added to a 1 liter solution. So what we need to think of this as a buffer solution that has both your sodium propanoate as your base and your HCl as your acid. Okay, so here we go. So again, I'm going to start off with my buffer formula, which is H plus equals the Ka, and the Ka was given to you. I'll give it to you. Ka times the ratio of the weak acid over the weak base. Okay, and I guess that really, it could be in brackets, but we're going to change it over to moles in a little bit anyway, so, but I'll keep it in brackets here. The Ka was given to us as 1.3 times 10 to the negative 5. Okay, so this is how I'm going to start this whole problem out. I'm going to have my 1.3 times 10 to the negative 5 or my Ka over times the moles of weak acid. So the only moles of weak acid that we have in the space so far at this point is just the 0.02 moles. Okay, that's the only acid that we have in there. The rest of it is all from here. So then that's my base part. So I'm going to subtract what I started up. My original molarity, or original number of moles, is 0.1 moles. That's my mole base, minus the amount of acid I put in there. So then we're going to get H plus. H plus is going to be equal to 3.25 times 10 to the negative 6. I can convert H plus to pH. pH equals the negative log of 3.25 times 10 to the negative 6. And so that should equal to 5.49. Okay, so we're going to do number 27D. 27D says to calculate the mixture containing 0.100 molar of propanoic acid mixed with a 0.100 molar sodium propanoate after adding 0.020 moles of HCl to a 1 liter solution. So what I already did is I just calculated out the number of moles of the weak acid, the weak base, and I wrote down how many moles of HCl was given, just so that when I'm doing the weak acid and the weak base calculations, it'll make a little bit more sense on why I'm adding and subtracting. So again, we're going to use the buffer formula. So I have H plus equals the Ka, and Ka is given to you in the book. It's 1.3 times 10 to the negative 5 over the moles of weak acid. So first off, we're going to have to do some adding here, because originally we have 0.10, and I'm just keeping the significant figures here, 0.1 moles of my acid, and I'm adding more acid to it, so I'm going to add the number of moles of hydrochloric acid we have in here. So now you understand that what's going to happen is that acid that's been added is going to be it's going to react with the base that's in the solution, so that's why we have to subtract the number of moles of base. So I'm going to subtract 0.020. And when we do all calculations, or overall calculations, I'm going to get, let me see, why don't I give you a little bit of time to you do it. Okay, so are you with me? So I'm thinking that you got the correct answer is 1.95 times 10 to the negative 5 as your H plus concentration. You can easily convert your H plus concentration to your pH by taking the negative log of 1.95 times 10 to the negative 5, and that's going to equal a pH of and are you doing it with me? It helps out more if you do it with me. pH equals 4.71. Okay, problem number 53A. It says to consider the titration of 40 mils of a 0.2 molar perchloric acid by 0.1 molar KOH. Calculate the pH of the solution when 0 milliliters of KOH have been added. So we're going to do a couple of these because they say calculate the pH when 0 mils of KOH is added, when 10 mils of potassium hydroxide is added, 40 mils, 80 mils, and 100 mils of potassium hydroxide is added. So there's several different points along this titration curve that they want you to calculate the pH. So we're going to do the first one, 53A. So the first thing we need to look at is what type of acid and what type of base are being titrated together. Well, you know that this is a strong acid, perchloric acid is a strong acid, and you also know that KOH is a strong base. So there's a couple things that you know immediately. You know that the pH at the equivalence point is going to be 7 because you have a strong acid and a strong base based on definition. So I'm going to write a couple of things in here just so that we kind of remember stuff. All right, so let's see. We have a strong acid and a strong base. So at neutralization, pH is going to equal 7. I want to put that in the same line. Let me make it smaller. pH equals 7. Okay, you also know that at your equivalence point, your moles of acid will equal your moles of base. So at equivalence point, moles acid equals moles base. Something else to be reminded of? What else? Oh, whenever you're doing these types of titration, always keep in mind the total volume of the solution. So always keep track of the total volume. What else do we know? We know if we have a strong acid and a strong base, your net ionic equation is going to be your H plus OH forms water. And I think that's about it. I think that's about it for now. So for the first part, I don't think we need to use all this information, but for the first part it says what is the pH of the solution when 0 milliliters of KOH have been added. So that's the easiest part, because all we have to do is calculate the pH of the strong acid. And you guys know that the molarity of a strong acid is going to equal the molarity of the hydronium ion concentration, because strong acids will completely disassociate. I don't know if I need that M. I'll put that M there. So now we can just take the negative log the pH equals the negative log of 0.200, and that's going to equal 0.699 for my pH. Not too bad for that type of problem. Now the next problem, a little bit more difficult, but not that much. You guys can do it. I do need to add a little disclaimer at the end of this, because your molarity of your strong acid will equal your hydronium ion concentration only if you have a monoprotic strong acid. And so all of your acids are monoprotic with the exception of, which one? Yep, that's right, H2SO4. So that's the only one that has the exception. Sorry about that. And now we'll go on to do more calculations along this titration curve. Okay, so this is 53B. We're doing the same titration, 40 mils of 0.2 molar perchloric acid. We want to calculate the pH of the solution after adding 10 mils of KOH, or potassium hydroxide, to the solution. So a couple things that we want to keep in mind. This is a strong acid and strong base, so the calculations that we're going to do are stoichiometry type calculations. We don't need to worry about buffer problems here. We also want to remember that the total volume of the solution now is 40 plus 10. So total volume, I'm just going to write that here. Total volume equals 50 milliliters. Okay, so let's just get started. So we know that your ionic equation is the acid hydronium ion plus your hydroxide is going to form your water. So we're going to get the H plus concentration from the acid, the OH concentration from our base that we're adding, and remember this is kind of like a limiting reagent problem. We're going to use up all of the base, and once we have used up all the base and neutralized whatever acid we could, the leftover hydronium ions that are left, the excess hydronium ions, are going to be the ones that are going to be used to calculate the pH. So we do have to convert to moles to figure out how many moles of acid we have, or how many moles of hydronium ions we have, and how many moles of hydroxide we have. So I'm going to keep it in millimoles just because it kind of makes it a little bit easier. There's one less calculation to do if we keep it in millimoles. We don't have to worry about dividing or multiplying by 1,000. All right, so we have 40 milliliters of a 0.2 molar solution. So if I multiply 40 milliliters times 0.2, I get 8 millimoles. So I have 8 millimoles of acid. 8 millimoles. Now I'm going to do the same thing with my base. I have 10 milliliters of the KOH, and I didn't write it down on my problem, but the molarity of the KOH is 0.1 molar KOH. So I can use that to calculate how many millimoles of KOH I have, and I have 1 millimole. So I'm going to use up all of my base, millimole. I'm going to use that all up to neutralize the acid. So if I use 1 whole millimole up, I'm going to neutralize 1 millimole of acid. So I'm going to subtract. So what am I going to have left over? I'm going to have 7 millimoles of acid left over, and that's what's going to contribute to my H plus concentration. Okay, so now I'm going to put it all in one formula. You guys know that the hydronium ion concentration is going to equal the molarity of the acid. I have 7 millimoles of acid. There's my total volume. So I'm going to do this. pH equals the negative log of my concentration of the acid that's left over. So 7 millimoles moles over volume, 50 milliliters will give me my molarity, right? And my molarity of the acid is going to equal my molarity of the hydronium ion concentration, and the negative log of that will equal my pH. So my pH is 0.854. Okay, so we're going to work problem 50, what is this, 53? 53D. So what I want to think about is all the different points along the titration curve. And in this case, I'm going to look at the amount of milliliters of base that we're adding. So I already know that I have a total, because we calculated it previously, we have 8 millimoles of acid. I'm going to calculate how many millimoles of base I have. So we have 80 milliliters of base of a 0.100 molar KOH. KOH. So that's going to give me 8 millimoles. So when we have 8 millimoles of acid and 8 millimoles of base, what point are we at? We're at the equivalence point. Okay, so there we are. We're at the equivalence point. When moles of acid equals moles base. Mole acid equals mole base. And if we have a strong acid and a strong base, so strong acid, strong base, equivalence point, we know that the pH is 7. There we go, that's it. Okay, we're going to do 53E. So here we are. Same problem, same molarity of KOH, except this time we're adding 100 mils of KOH. So we know we're past our equivalence point. We know that the total volume is going to be 140 because it's 100 mils of KOH plus 40 mils acid gives us 140 total mils. Let's see, but this time, since we know we're past the equivalence point, we're not going to be calculating the hydronium ion concentration. We're going to be calculating the hydroxide ion concentration because it's the hydroxide that is in excess this time. So we still have 8 millimoles of acid, but now we have 10 millimoles of base, and that millimoles is coming from 100 right here, 100 milliliters of a 0.1 solution. So I'm calculating the number of millimoles. So we're going to use up all the acid in our neutralization. So we got that. And we're going to use 8 millimoles of base, and we're going to have 2 millimoles of base left over. So this time, since we have base, we're going to calculate the OH concentration. And if I calculate the OH concentration, then I'm going to have to solve for POH and then subtract 14 minus the POH to get pH. So POH equals negative log of my molarity of my base. So that is 2 millimoles, because remember, moles divided by liters is molarity. Since I millimoles and milliliters, I could just divide those out. And my pOH is going to equal what? You do it. What is my pOH going to equal? Negative log negative log. So I'm getting 1.845. I'm going to round to 3 sig figs because it looks like I have 3 sig figs there, there, and there. So pOH is 1.845. Then my pH is going to be 14 minus 1.845, which is 12.155. Okay, so those are calculations along a titration curve with a strong acid and a strong base. Now I'll do a couple of problems with a titration curve with a weak acid. What's next? Okay, so we're going to do problem 55B. This is a titration with a strong base, right here, and a weak acid. So when we're using strong base, weak acid, you're going to be using the buffer formula. Your Ka is given to you as 1.8 times 10 to the negative 5. I know this is negative 5. This program doesn't allow me to type in superscripts, so forgive me. So this is what I'm going to do. First thing I'm going to do is I'm going to write in my buffer formula. H plus equals the Ka times, well, let me actually do it correctly. Okay, the weak acid over the ratio of the weak base. Now, since we are adding base to this whole formula, we're going to need to remember that we're going to add to the acid because we're we're not adding to the acid. We're going to need to add to the base and subtract from the acid because the acid that's here is going to neutralize whatever base that we're adding. So, okay, so let me see, H plus equals 1.8 times 10 to the negative 5, and I get my weak acid. I'm going to convert to moles. Actually, I'm converting to millimoles. So, my weak acid is going to be, where's my weak acid? It's going to be 20 millimoles. That's my 20 millimoles of acid, and I'm going to subtract out the amount of millimoles of base I've added, and that would be 5 millimoles of base. Then on the bottom, I have, I know this doesn't seem right, but at first we don't have any base in there. Then I'm going to add how much base I add into the solution, which is 5 millimoles. So now we're going to just solve for H. H plus is going to equal what? So if I plug all this into my handy dandy calculator, you do the same thing. And you'll beat me. But I'm going to get 5.4, how many sig figs? 2, times 10 to the negative 5 for my hydronium ion concentration. My pH is going to be the negative log of my hydronium concentration, which equals, pH is going to equal 4.2 sig figs. I'm getting 2.7. Okay, so for this section of 55, part C, I want to always kind of keep track of certain points along the pH curve. One of the major points is I want to know when the equivalence is going to occur. So what I did here is you guys know, we all know that at the equivalence point, the moles of acid is going to equal the moles of base. So, based on this information right there, that gives me 20 moles of acid. So that means I need to have 20 moles of base to get to the equivalence point. Okay, so I know that. Now I know that my concentration of the KOH solution is 0.100 molar KOH. So if I can figure out that I need 20 millimoles of base to get to the equivalence point, I can use this formula right here that comes from the molarity equation to solve for the volume of the base at the equivalence point. So I know ahead of time, now that when I look at the rest of these problems in the book, when I get to 200 milliliters of base, I know I'm at the equivalence point. But that also gives me another useful information. Because for weak acids with strong bases, there's the half equivalence point that's pretty important as well. So the half equivalence point is just going to be half of this right here. So when I have a volume of 100 mils, so 100 mil volume of my 0.1 molar base, which is my KOH, lets me know that I'm at the half equivalence point. So this problem is a little bit easy, or not really easy, but this problem you're doing a little cheer because you're like, oh, good, not a whole lot of math here. Since adding 100 milliliters of the KOH to the solution is going to put us at the half equivalence point, then we know that the H plus concentration is going to equal the Ka. And the Ka is given to you. Ka from the book is H plus is 1.8 times 10 to the negative 5. So then once we have the Ka equaling the Kh, then you can just find pH. pH. Getting a little tired here. So my pH again is negative log of 1.8 second EE negative 5. 4.74. How many sig figs? 2. 4.74. I'm going to keep it at 2 sig figs because the Ka was given to me in 2 sig figs. Alrighty, last problem, last homework sample problem of the day. So this is where we have a weak acid with a strong base and we're at the equivalence point. So when we're doing the equivalence point, we are actually taking the pH of the salt solution because all of the acid and all of the base have been neutralized. So what we're going to do, here I'm going to write out the equation. So we have C2 H3O2 negative plus H2O is going to form my OH concentration plus the acetic acid. HC2H3O2. Alright, so looky here, we have OH being produced. So since OH is being produced, what do we use? We don't use Ka, we use Kb. So I'm not going to calculate Kb. I'm not going to show the work for calculating Kb. You guys know how to calculate Kb from Ka. So I got 5.6 times 10 to the negative 10. Okay. Let's see, what else do we need to do? We still have to look at total volume now because we are going to use the molarity of my C2H3O2, my acetate ion. So, what do we have? We have 20 millimoles. Yep, we have overall, remember we have 20 millimoles of acid, so we have 20 millimoles, but the overall concentration is going to be 20 millimoles over 300 milliliters because we have to add. So my molarity is 20 millimoles to 300 milliliters, which is going to give me 0.067 for my molarity for this. I think the rest of it, all we're going to do is we could erase it, and then we can find out the OH concentration. But you guys know how to do rice tables well enough. So I'm going to just go right into the problem. So we're going to have our KB, which is 5.6 times 10 to the negative 10 equals x squared over my molarity, which is 0.067 minus x, and we're going to neglect x. Okay? I'm running out of room. I'm going to have to go to a new slide. Okay, so I think this is where we were on the last slide. KB equals x squared over 0.067 minus x. We're going to neglect x and come up with this equation right here. From here, that's going to equal we're going to cross multiply 3.75 times 10 to the negative 11 is going to equal x squared. Let me just double check to make sure. Okay, 3.75 times 10 to the negative 11 equals x squared. So take the square root, both sides, to get your x. X is going to equal 6.13 times 10 to the negative 6. And remember, this is your OH concentration, because we're using KB. So then my POH is going to equal 5.21 negative log, double check that, 5.21. So then my pH equals and you got it if you put 8.79. So some of the things that you need to remember when we're doing the equivalence point with a weak acid is we're doing the hydrolysis equation. The initial molarity of the salt is going to be number of millimoles divided by total volume, and that'll give you your molarity of the salt. And that's how we calculated this thing right here. So hopefully this will help you out. For those of you who didn't understand the homework, had trouble with the homework, hopefully these sample problems will help you out, and so that you can finish the rest of them. Again, please show your work. Please. Okay, have a good day. I'll see you tomorrow or Wednesday.